Welcome everyone. This talk is about deploying apps and services using ArcGIS API for Python. I am Atma Mani, and I am joined by my colleagues Akhil Negi and Divyansh Shah for giving this talk. The Python API is quite popular for its data science and automation capabilities. However, it has a third aspect to it, its ability to build lightweight and scalable web applications. The intention of this talk is to throw some light on that and showcase some example applications. This is the outline of the talk, which goes on for about an hour. We have grouped it into three main parts. In the first part, my colleague Divyansh would take us through the apps module of the Python API and explain what it means to build applications by using the API and demonstrate a few different applications he built in that manner. Next, we switch gears and talk about building services. This is a broad topic, so in the first part, I will talk about building geoprocessing services that can be published on ArcGIS servers and consumed by other ArcGIS applications. I also talk about alternate mechanisms of deployment, such as deploying on your own web servers or deploying on servers borrowed from a cloud infrastructure. With that as a foundation, in the third part, my colleague Akhil will talk about deploying services on function as service infrastructure. He would start with a simple example to explain the concepts involved, but then quickly show how even complex deep learning applications can be deployed in such a fashion. If you are new to the ArcGIS Python libraries, I am hoping to give you a really brief and a quick introduction in this slide. At Esri, we have made deep and early investment in Python, and so Python is a preferred scripting language in ArcGIS. As a result, Python can be seen in various applications throughout the ArcGIS ecosystem. This slide is a layout of those various applications. If you notice, Python has a dual nature. It is a premier language for data exploration and analysis, where it is used in an interactive or hands-on fashion. The other nature is that it also makes for an excellent medium for scripting and automation, where the typical use case is to build and deploy your application as a service on a server and let it run on demand for multiple users or let it run on a schedule. So in this talk, we're going to talk about the latter aspect of it. When we talk about ArcGIS Python libraries, we talk about two premier ones, the ArcGIS API for Python, also called the Python API, and ArcPy. The ArcGIS API for Python, at a high level, can be explained as a library that you typically use to work with your web applications or WebGIS. The ArcPy library is a library that you will use for ArcGIS desktop applications like ArcGIS Pro. In this talk, much of this talk is going to be using the Python API for building apps and services. The Python API has some unique features to it. It is a pure Python library, which means that it is OS agnostic and we can install it on Mac or Windows or Linux. The last part makes it very suitable for deploying it on servers. And it is also lightweight and modular. That means that if you do not use the full capacity or full functionality of the API, you don't have to install all its dependencies. You can only install the ones that you're needing for your application. That way you can make the package very lightweight and nimble. And it is finally free of cost. With this real quick overview, I'm going to turn over to my colleague Divyansh to talk about building applications.
Now we will talk about how to deploy apps in ArcGIS API for Python. Before that, let's look at the various modules that are present in ArcGIS API for Python. This is the GIS module, which is very important as it handles all the users, groups, and contents within your GIS. These modules in greens like raster, features, learn, the functions, the tools that are in them, they help us process various GIS dataset, and this learn module helps us do even deep learning. These modules in blue, they help us for our additional workflows like geocoding and geoenrichment. These modules in orange, they are basically for visualization and for managing various apps. Using the API reference, you can see this comprehensive list of all the modules that are present in the API. And you can go to each one of them and see their documentation and the use cases. We also provide the samples and guides for additional documentation and to give a head start in your workflows. So today we are going to talk mainly about the ArcGIS.apps module. It contains various functions and submodules for managing apps such as dashboard, workforce, story maps, survey 1 to 3, etc. So let's start with survey 1 to 3 for ArcGIS. So Survey123 is a form-centric data collection platform. So it helps you to create smarter forms, and it can be used to collect data from the field using various volunteers and workers. The best part about it is that it can be supported on both web and mobile devices, which gives us the flexibility to perform the surveys in an online or an offline method. It can be readily integrated with ArcGIS Online and ArcGIS Enterprise. Survey123 has various applications like in disaster response and inspection of utilities. So here is one example where Survey123 is integrated with ArcGIS API for Python and is used for collecting data about plant species. Let's see how ArcGIS.learn can be used to enhance surveying workflow. Here you are seeing how Survey123 is used to do a tree inventory. My colleague Sandeep is doing field data collection by visiting each tree and feeding in the species name. But he is not a trained botanist. He does not remember all the species by heart as there are thousands of them. So what can we do to identify these species automatically? The notebook here uses the Learn module of ArcGIS API for Python to easily train a deep learning model to identify plant species from picture of their leaves or flowers. Here we use an openly available dataset containing 260,000 images across 10,000 species. Here we are creating a plant classification model and we specify the backend to be TensorFlow. We then use the fit function to train the model. After the model has been trained, we can see how the model is doing a great job in identifying all the different species. Once we are satisfied, we can save it as a compressed TF-Lite model and it's ready to be deployed on mobile devices. The surveyor can then start the Survey123 app on their phone, open the survey and begin the tree inventory. And instead of scrolling through thousands of species, they can simply point the camera at the leaf of the plant and they are done. The deep learning model correctly classifies and fills it out the form by eliminating the need to go through that long list of plant species. The model is running on the phone itself in a completely disconnected environment. And after completing the survey, we can connect back online and share the data on the organization's portal. This data layer is feeding the web app where we can observe the results of the survey. For each location, we can click to find the picture of the plant and its classification. By integrating ArcGIS with Survey123, we are putting the power of deep learning on the edge devices and solving important problems. Now, let's move to ArcGIS dashboards. A dashboard is a great way to share key insights from our data in the form of charts, maps, etc. They're extremely useful information providing tool, as we must have realized from this COVID dashboard, which was created by Johns Hopkins University. This dashboard is providing so much information in just one single screen. They're extremely helpful in monitoring and managing operations and visualizing performance and summaries, etc. Usually, these dashboards are created by GUI tools, but we've recently added the support to programmatically create these dashboards using ArcGIS API for Python. In this notebook, we use the change detector class from ArcGIS.learn module. This change detector class is used to detect change in building footprints. I've already got a pre-trained model, which I've produced using this sample notebook. You can also use this sample notebook to get your own pre-trained model. Once I have that model, I use the two local rasters that I have. The input to the change detector model is an image from a before timeline, an image from a later timeline, and we can predict on that. Here I'm specifying save equal to true because I need this change label to be saved on disk. Visualize equal to true says that it will be visualized in the notebook. And this crop predict helps when the raster is too big, the raster is cropped and then predicted and then stitched back. I've already published all of them as a web map. Now I want to share the results, and one of the best way to share results is using a dashboard. I will create a dashboard right here in this notebook. I will import the dashboard class and other necessary functions which we will look at. First, I get the web maps, I create their objects, and I set their height for visualization in the dashboard. Here I'm specifying, here I'm creating an indicator where I'm specifying that I have this item called after change, which is actually a web map, and we specify that we want to show the total change area. We say that the value type is statistic, and what we need to do is to take the sum. Here I'm specifying this shape area as this is my value field on which the sum needs to be calculated, and specify the height, and I can visualize this indicator right here in the notebook. Since web map is incomplete without descriptions and text, so we can actually specify these descriptions right here. As you can see, I am specifying some headings, uh, and you can even visualize headings here in the notebook. Then we have two maps, one on the left which is a before change map and one on the right which is after change map. And what I can do is I can sync them. Here I'm using this sync widget tool to do that. And I'm also updating the indicator based on that. Now that I've got all the necessary parts, I set up my dashboard. I set the layout of the dashboard. I add a row where there are two columns, one which contains these things and another column which contains these things. So this column corresponds to this left column, and this bottom corresponds to right column. And when I add row, it inserts this row. Using these two functions, you can create layout of your choice. As you can see, I visualize this dashboard right here in the notebook. Once I'm satisfied with the layout, I can save and publish the dashboard. So here is that dashboard. As you can see, the maps are synced. If I change this, the area also gets changed and everything is synced. Here is how you can use the Dashboards API to create your dashboards automatically. Now let's move on to another app called ArcGIS StoryMaps. ArcGIS StoryMaps is a great way to tell convincing stories with the use of maps and narratives. We can share our analysis in the story maps. We can embed maps. We can embed pictures. We can tell a complete story around an analysis in a convincing way. As we saw dashboards, we can bring multiple such dashboards within the story map and we can share all of them at once. Now, let's look how we can integrate ArcGIS API for Python to iteratively create and update these story maps. Here I'm showing an example of one of our users who is Alaska's Division of Community and Regional Affairs in the Department of Commerce. They have an online database which makes information available for dissemination for each one of their 347 communities in which the state's population live. For each community, there is valuable information and a story map link that provides additional information. Let me show you one of the story map of Big Delta community in Alaska. You can see that this story map is beautifully created. It has mixed media and a rich table of content. It takes a lot of effort to bring one of these story maps to life. One has to integrate information from variety of sources, think about cartography and think about presenting it in a compelling manner. And imagine doing it 347 times for each one of their communities and updating them when there is an underlying information that change. This calls for automation, and that's what the GIS analysts at DCRA did. They have authored a Python script which uses ArcGIS API for Python and the story maps module. Here, they're connecting to their GIS and defining some utility functions. The core of this code lies here, where they are cloning an existing story map and then setting their base map layers. This clone items functions recursively clones each item present in the story map, whether it be web map, dashboard. Here they are setting the base map layers, setting the photo link which forms the context of the story map, and finally setting the table of the content. Once this is done, repeating this for the next 346 counties is just a simple Python for loop. Here is how you can use the story maps module to regularly update your story maps. Now that we have seen how to integrate ArcGIS API for Python with the apps inside of ArcGIS like dashboards and story maps, let's see how to integrate it with apps which are outside of ArcGIS like Streamlit. So Streamlit is a very fast way to create web apps in few lines of code. It is a very easy to use simple API and can be deployed very quickly. Its major applications are in data-centric apps like data annotations or deep learning model deployment or any other such tasks. We have created a demo where we have integrated ArcGIS API for Python with Streamlit for the task of scanned map digitizer. In this use case, we have paper maps containing locations where specific species of animal or plant is found, like this one. The task is to scan these maps, georeference them, and use this for different analysis. Doing this manually for all the different species is a very tedious task. For this, we have created this sample notebook where we use the scan map digitizer class in ArcGIS API for Python to georeference these species locations and put them on map. So it basically consists of 5 parts. The first is to create the mask of the actual species location, which is the green area. Here we have the binary mask for that. Second, we create the template image, which is actually the whole area which we want to find. Third is to prepare the search region, which is the world map, and we have converted it into a binary form. The fourth is to do the actual template matching. So here is our search template and here is the search region. So this is the area where the template has actually matched. Fifth is to actually georeference them. So we know the coordinates of this map. We can apply these coordinates to the newly found area and we will have the digitized version of this. So converting this into a GUI tool using Streamlit is very simple. So here is the graphical user interface of our app. Let me show you how I created it using using Streamlit. Here you can see that I've created this column where I'm asking for these inputs R, G, and B. I've added a couple of sliders and I've added a Dropbox. Now I'm initializing the scanned map digitizer class, which we saw in the notebook. Using the user-defined parameters, we can just pass it in this method and we'll get the results. And we just do some post-processing, save the results in the file and all that stuff. And that is it. So let me show you the complete workflow. I will use this scanned map for my task. As you can see, initially it's not giving a great mask. Now let's tweak some parameters. So it has started to give the mask. Now, since this part is, I don't want the reverse, I'll just increase the dilation kernel and yeah, I can also increase the color delta so that it uses a wider range. Yeah, I've got this map now. So this is the scanned map and I will move to the next step. Now the template is here. Now I want the complete map of this thing. So I'll just increase some color delta. Yeah, and as you can see, It is doing fairly well on this. I'm satisfied and I can move to the next step. I'll select the world map image to prepare my search region. Let's see how it gets binarized. So this looks good to me and I can proceed. As you can see, I've specified the uh, spatial reference and the extent. The search region is complete and I will now match the template. So because of the good initial defaults, it was readily able to match this template right down here. And I'm satisfied. I'll just digitize this image. So as you can see, this green area has been beautifully put on this map, and we have also dumped its shapefile, and that's ready to be visualized in ArcGIS Pro. As you can see, the species Sactostomus campestris has been correctly placed in this world map. And if we have multiple of these, we can create a beautiful map where we have all the species of different types of plants and animals. So here is how you can include GUI apps like Streamlit or even PyQt with ArcGIS API for Python.
Thank you, Devansh. That was a really good introduction to demonstrating how applications can be built using Python. In this talk, in this part of the talk, we're going to switch gears and talk about how services can be built using the Python API. Before we get started, what is a service? A service can be defined or considered as a pattern of developing or deploying applications using a client and a server infrastructure. So there are two parties involved here. And the communication between these two happen over the web using HTTP protocols. How exactly does a service work? Well, the user interacts with a client, which is usually in the form of a web application. This client application will send the request over to the server using the HTTP protocol that we discussed earlier. The business logic and all the computation and the geoprocessing will happen on the server. The server will send the response back to the client application, and the user will see the response through the client application. What are the differences? What are the advantages of building things as services? The first and the biggest advantage is that the user does not have to install any kind of a software. If you're building web applications, then all that the user needs is an internet connection and a browser. So this way you can serve multiple users, no matter what their hardware is or what their software or operating system is. And you can serve all of them at the same time. And if your number of users should increase, and it is very easy for you um, to horizontally scale or increase the number of servers on the server side, then asking the users to upgrade their hardware or buy expensive hardware and software combination. To understand deploying services better, we'll use an example application. Have you ever looked at a photo or vacation photo and wondered where was that photo taken? How nice would it be if you can build an application that will read the metadata from the photo and embed maps and location or address information right onto the photo? We can do that these days because modern cameras and cell phones will store GPS coordinates along with many other information into the metadata region of your photo's data structure. Then we can use some appropriate library to read that information and make a map out of it. So our workflow will look something like read a photo and read the metadata information out of it, extract the GPS location coordinates, make a map of the region, run it through reverse geocode to get address or point of interest labels for the photo, and embed all of that back into the photo. And for this application, we'll take a few different approaches. We will build it as an ArcGIS Pro application. Then we'll publish as a GP service on your ArcGIS enterprise infrastructure. Then we will also look at how we can build it using a Flask based service that you can deploy it on your own server infrastructure or the same thing that you can be deployed on a cloud-based infrastructure like Heroku. Before we build a service, we need to prototype what the service is going to do. And for that, we're going to use a notebook. We are going to import a lot of different libraries. Primarily, it's going to be the ArcGIS API for Python for doing all the kinds of geoprocessing work. And we're going to use a library called Pillow for image processing. In the first step, we are going to read the image file and we can preview it nicely within the notebook. This is one of my vacation photos, but I have forgotten what the name of the falls is or where I've taken this photo. And let's see if we can find both of that information and help me out. To get the EXIF information, we can use an API like getEXIF. And if you have looked at EXIF information before, you would notice that it's pretty cryptic. There's a lot of these code labels, and the values are also not easily interpretable. So let's write a different simple helper function that will convert and extract the GPS location information out of that. Now, when we run it, we are able to find the GPS latitude, the longitude, and a few other information. Let's write another helper function to decode this information into a much more user-friendly format. So with this, we know that the values are in decimal degrees, the latitude and longitude and latitude, as well as the elevation in meters in the GPS coordinate system, and the bearing information from the camera's internal compass. Now that we have the location, we can go ahead and reverse geocode using the geocoding module of the Python API. One nice feature is this feature types parameter. So it allows me to specify what kinds of databases the reverse geocode on the server should to look into. Because I'm using my vacation photos, most of these are points of interest or they are street addresses. Sometimes it is locality if it is outside the United States. And then we compute a little bit, and then we can produce what the output has to be. So in this case, it's the town of Genesee in New York, which is more or less where the location where the photo was taken. The next step is we can go ahead and make a print out of that. So we compute a web map object out of it. We just create an empty web map, customize the street map, base map information. Using the point X and Y, we are making it as a feature and adding it to the web map. Then I'm writing a simple function to compute an extent, because when you ask the server to print, we need to give it the location of the center of the photo, center of the map, as well as the extent that it wants to print. In this case, I'm making it very simple by computing plus or minus 0.1 degrees latitude and longitude. With that, we can call the print method of a web map object. This is a new method that we are adding in the upcoming version of the Python API. So with this, the server will render the web map on the server side, and it will print it and then send you back a URL for the image that you can download. Here, I'm previewing the map right within the notebook. Now we have the address information as well as the map image, and all we need to do is just do some image processing and paste it into the photo itself. We start by composing a dark or translucent rectangle for the text to appear better, and then we compute or we make a canvas object, and then we choose the font size and type of font for typing in the address information. We choose the location where it has to go, which is the offset, and then we can write it right onto the photo. Next, what we do is we do the same thing. We compute the X and Y location for pasting the map. And I found that the bottom right corner is aesthetically appealing if you want to put these map and text. And finally, we call the paste method, and we can paste the map right onto a copy of the photo object. And I'm also using a little bit of blur effect to make the transition a little bit more appealing to look at. And now we can preview the photo, the map, and the text right within the notebook. If everything looks good, I can go ahead and save it to disk. That's it. We have prototyped what the service needs to look like using a notebook. Next step, we are going to take the same thing, but break it down into different functions, and we can make a GP tool that is running in ArcGIS Pro. So far, we have seen the prototype of what the service needs to look like in a notebook, and we want to publish that as a GP service on the ArcGIS Enterprise. The easiest way to do that is to first make a Python toolbox in Pro and publish that toolbox as a service. Making a Python toolbox in Pro is pretty easy. Once you have your home folder, you just need to right-click New and say Python Toolbox, and that creates you a toolbox with a .pyt extension. And when you right-click it and click on the Edit, you will notice that it will open it in your favorite text editor. The Python Toolbox is actually a Python file, but with a .pyt extension that ArcGIS Pro can interpret and build a nice user interface. To the end user, it just looks like any other tool that is built with ArcGIS Pro, except you define what the tool needs to look like. So the tool has a toolbox class, and then there is a tool class. There are multiple such classes that can be there within the tool. And then there are some basic information that you need to pass there for ArcGIS Pro to make a tool out of that. And you put all the computation into the execute function of the tool itself. So I went ahead and I broke down the notebook into a Python tool, and this is the tool that I just created. So let me walk you through what it looks like. Let me close this one out. And so I have my Sublime text editor. So let's help it out by giving it the syntax as Python. Okay. So now here I have the toolbox, which is a compulsory class. And then I have my tool, which is called embed photo. So here I have a function called getParameterInfo, where I tell it the input and output parameter for this tool. And I can specify some kind of a filter. So the UI itself will prevent users from picking illegal file types like text files or markdown files or something else. They can only pick JPEG or JPG files. And I also tell the type of the output file is also a JPEG file. Then I went ahead and created a lot of these functions, which are very similar to what we saw in the notebook. like a function to read the EXIF information, to perform reverse geocoding to get the address, export the map into an image, and finally embed everything into the photo itself. In the execute function, I'm calling all of these one after the other, and I'm using something called messages.addMessage to add informative messages to the tool when it runs. So with that, I can save this file, and I can refresh my toolbox to get this tool. I can click on it and see this is the user interface that Pro has already built for us. It looks very much similar to a regular tool that comes in ArcGIS Pro. I can choose input image, let's say something like image number 5. I don't know what it is, but image number 5. And we can choose an output location. So let me make sure that I'm not overwriting something. Output images, out2.jpg. Then we can hit run. As it runs, we can click the view details and look at the messages that our tool is printing. That's it, it finished. You can see that it extracted metadata, it obtained the address information, and it is output the image. I can open the output images, and here's the output photo. Yeah, so this is the Bixby Bridge in California along the Pacific Coast Highway, and you can see the map of that. And if I zoom in sufficiently, you should be able to see a text information at the bottom right corner. There we go. Oops. Okay, zoomed in way too much. California in March 24. Now that we have built an ArcGIS Pro Python tool, the next step is to just go ahead and publish it as a GP service. To do that, I just sign into an ArcGIS Enterprise with the appropriate privileges to publish a GP service. And to publish, all you need to do is go to the History tab in geoprocessing, pick one of these successful runs. I've been trying it quite a bit, as you can see. And you can hit the Share As and select Share Web Tool. And that brings you the publishing or the sharing dialog, and you can go ahead and plug in all the different details that you need to make it as a web tool. Things like the summary, tags, and a few other information. Then you can click on Analyze to find if there are any errors and rectify them. So I went ahead and did it and published that as a GP service. So this is the service on my portal, and when I click on the Open in Web Map Viewer, it'll open up the typical Map Viewer application. But it has the analysis selected, and it would have the toolbox up here, along with the standard tools that come with the default enterprise. I can expand and I'm able to see my task or the tool here. Here I can give a path to a URL to a photo, or maybe a path that is accessible to the server, and click on Run Analysis, and then it performs the analysis, gives me back the output. Because this is a GP service, any ArcGIS application can use this service by default. So for example, if another user who does not want to run it on the web wants to use ArcGIS Pro to run the tool that you're authoring, they can very well do it. It's pretty simple. So go to the catalog pane and go to the portal tab, and when you refresh, you should be able to see the toolbox or the tool that you just published. Here is the tool that we just published, and we can see the task. We can select the photo, hit run, and we'll be able to perform the analysis on the server side. So this is a really quick example of taking a notebook and publishing as a web tool to run on the server. It runs as a service on the server. So far, I've shown you how to deploy a GP service on an ArcGIS enterprise infrastructure. What if you do not have an ArcGIS enterprise? What are your options? You can build your own standalone web application using frameworks such as Flask, and that's what I'm going to show you in this demo. Flask is a popular web application or a web development framework for Python, and it is extremely beginner friendly, and that's what I'm using now. So here I have my PyCharm IDE, and there are some important things, basic things when you wanted to build some things with Flask, such as defining your API endpoints. So here I have a few different ones defined. This is the root whenever the users hit the home page of the application. Then I have a few other endpoints, like the embed endpoint, which in my case is the one where all the different computations happen and the photo and the map gets embedded in the photo. And I have a few other endpoints that are supporting this whole endeavor. So when the user comes to the home page or the root, the function that is defined right under the decorator gets invoked. That's the job of the Flask framework. And in this case, I'm keeping it pretty simple, where I'm just rendering a HTML page. And this HTML page is also simple. It just has some pictures to explain what the whole website is about, and it has a button that asks the users to click on if they want to embed things into their photo. When they click on that button, it calls the embed endpoint. It actually calls a file upload endpoint, and the upload button on that calls the embed endpoint. which will promptly invoke this function and pass all the input parameters that the user is passing to it. This embed is pretty similar to what we have been seeing so far. Um, it has logic to read. It calls a function to read the GPS data and get the from the EXIF metadata information, reverse geocode to get the address, and then compose or export the map, and finally embed everything into the map image. And everything goes well, it will render another HTML page that contains the input photo on the top and the output photo at the bottom. The rest of the file should be very familiar to what you have seen so far. The get GPS info will have functions to read the image, extract GPS information, convert that to decimal degrees, and so on. The render map has the logic to compose a web map and print it on the server side and get a JPEG image that you can put it on the map. The reverse geocode will do just that. And finally, the embed function uses the pillow library to take all of these maps and text and bake it right into the image itself. Then, to run this application, I can just hit on run, and Flask will start up on a local server on my computer. This is the URL to it. And this just opens it right up on my browser. You can still see that this is running locally on my computer. And when the user click on the convert your photo button, we have this intermediate interface that allows the users to choose a photo. When they click on upload, it calls the embed endpoint, which will perform all the different computations, get the map from the ArcGIS online server, and put it right onto the photo. It just takes a couple of seconds. And now we can see the original photo here, and then we have the embedded photo at the bottom. So here we can see this is from Playa del Rey in California, and so on. So this was a quick example that shows how you can build a web application using a Flask framework in Python and use the Python API along with it. Now, if you wanted to deploy this on your server, you can just take this folder that contains all of these files and put it onto your server on which your web server is running, and users can just hit it at the server's address, and they can use this application. So far, we saw how to deploy a standalone application using Flask on your own infrastructure. What if you do not have a web server? Well, you can borrow a web server from the cloud, and that is exactly the kind of demo I'm going to show you. And for this example, I'm going to use Heroku as a cloud provider. So let us go back to my browser. Heroku is extremely beginner friendly, and that was the reason for my choice. And Python is very well supported within the Heroku platform itself. To get started, you would just go ahead and install the Heroku CLI or the command line interface. And then you would go and log in with your credentials for the Heroku account. The Heroku free account gives you a lot of free runtime, something that is totally within the scope. The application that you're building will be completely within this free scope that the Heroku provides. It's pretty generous. Now, once you have the application that you built using Flask, you need to do a few different things to make the app ready to be running on a cloud infrastructure. The first one would be to define all the project requirements using the in a requirements.txt file. So this is the pip freeze output that contains all the different libraries that you install to make this app running. Then in the runtime.txt, you specify a build stack. In this case, I'm telling Heroku to choose the Python 3.8.7 based build stack on which all these requirements will fit in nicely. Finally, you specify a proc file, which is very specific to the Heroku platform, and where you specify the web server that you need to run. In this case, I'm switching over from Flask to Gunicon, which is much more robust and ready for production deployments. And I'm specifying the start point, which is the app.py file. That's the file that will be invoked right after the deployment is complete. Now, once all these files have been added, you go to your command line. If you are familiar with Git command line interface, then working with Heroku is going to be extremely natural to you. So in your repo or in the folder where you contain all these files, so I can do an ls and show you all these different files I have. What you can do is you could do Heroku app create and give it a name. The name of the app within Heroku has to be completely unique across all the different users of Heroku. So you need to play with it a little bit to find out if a name is available or not. And when you click enter, Heroku will create an app for you, register that app URL, and keep it for you. What you do next is, I've already done it, so I'm not going to run it again. Here, once you've created the app, the next step would be to go ahead and push that to the Heroku Git remote. So let me explain what I'm talking about. When you create an app in Heroku, what it does, it registers Heroku as one of the Git remotes. So in the command line, if you do verbose, and you would notice that I have an existing remote on GitHub, and Heroku added another remote on the Heroku itself. So my project has two different remotes, which is pretty common. You can have multiple remotes for your repositories. So if you want to push this app onto the Heroku server, all you need to do is git push name of the remote, which is Heroku, and name of the branch, which is main, and hit enter. The moment you hit enter, Git will push all of this content onto the remote on Heroku, and Heroku will start the build process where it looks at the proc file and it looks at the runtime.txt and knows the build stack it needs to use. Then it looks at the requirements.txt file and starts installing line by line each of your dependencies. When everything runs successfully, it looks at the slug, which is all the different Python files in your repository, and it puts it into the container that is just installed, and looks at the proc file and it invokes the application. Then it gives you a URL that you can use and also give it to your customers. Anytime you have an update, all you need to do is just commit those changes locally and call git push main, Heroku main, and the whole application will just restart by itself, and it'll have all the updates that you have. So just to demonstrate the update part, I made a few different changes, like removing a couple of comments here and there, and I'm going to show you how it actually works. All these parts are very similar to how you would push to a Git local repository or remote repository. And now here is the Heroku part. So it knows what the build stack is, and then it knows that the Python application was detected. I did not make any changes to the dependency stack, so it knows that there are no requirements that have been changed. And then it does a few different maintenance updates, and then it's going to update the application itself. Okay, the Heroku has finished pushing my update up there. And then finally it gives me back the URL to my application. So I can copy this URL and put it onto web browser, and it will be the same exact application. So let's switch to our browser, and here we have our application. It's the mapinphoto.herokuapp.com. You can click on the button and upload a photo that you want to embed, and let's choose one of those photos. Now, unlike the previous example where all the computation was happening on the local server running on the computer, here the computation happens on the borrowed server on the cloud infrastructure. So here is my original photo, and then here is the photo with the embedded information, the map, and the city name at the bottom. So this was a really quick demo of demonstrating how to build a service using Python and deploying it on the cloud infrastructure. This URL is public, so if you're listening to this talk, you can head over to this URL, mapinphoto.herokuapp.com, and try it out with your own photos and see how well this application works. That gives you a brief summary of building app services using Python. To expand on this concept much more and to talk about building scalable services using function as service infrastructure, I'm going to hand it over to my colleague, Akhil.
Thank you, Atma, and hi everyone. Now we will be talking about deploying scalable services on FaaS infrastructure using ArcGIS API for Python. FaaS here stands for Function as a Service, and we will be using AWS Lambda to deploy serverless functions. We will start from very basic function deployment, and then we will keep on increasing the complexity from there. We'll take a look at implementing a geocoding service based on ArcGIS API, and finally we'll see how to create an address classification service on AWS Lambda with the use of ArcGIS Learn module. The service will be able to classify addresses into their respective countries. Let's get started with our first demo, where I'll be talking about the basics of AWS Lambda, and we will create a geocoding function, and that is capable of converting a string address into its XY coordinates. And we will also create a REST API gateway, which we will use to invoke the service and get the response. Here we are in the AWS Management Console. We'll go to the Lambda service and we'll create a function. We'll author the function from scratch, give it a name, and we'll select the runtime as Python 3.8 since we'll be writing the code in Python, and create the function. After the function has been created, we get a default piece of code loaded, and it just returns a hello from Lambda string in the response. We see that we have the main function with the name of Lambda handler, and it's within the lambda function.py file. And in the runtime, we have that information provided that the main function is Lambda handler and it's within the lambda function.py file, so that the trigger knows which function to invoke and within which file to invoke that function. Now let's create a trigger. We will go to add trigger and add API gateway. Then we'll create a REST API. We'll keep the security open for demo purposes. All right, the API has been created and added as a trigger to the Lambda function now. And here in the details of the API, we can see the API endpoint as well. Let's copy that and go back to the function. So once we hit the API gateway, it should return a response that says hello from Lambda. Let's try doing that in the browser window. And as expected, the function is returning hello from Lambda. Now let's see how we can pass custom parameters through the API gateway to Lambda function. So the event object here that is passed to Lambda handler function contains the query string parameters, and that has the query string parameters that are sent by the REST API gateway, and the context dictionary here has the metadata about the Lambda function. Now let's modify the code to accept custom parameters from API gateway and then process them. So now we have modified the function. We are getting query string parameters from the event dictionary, and we are getting a custom parameter named custom text from the query string parameters dictionary. And then we are converting the custom text into uppercase and dumping that into the response body. Let's deploy this. Once the changes have been deployed, we can modify the call. And as expected, the custom text is being returned after converting to uppercase. Let's go back to the function. One thing to notice is that the Lambda function by default only have access to the standard Python libraries, and in order to make external libraries accessible, there are two ways. The first one is going to actions here and uploading a zip file, and the zip file should contain the external libraries packaged in a zip format. And there is a limitation to the size of the zip file. The compressed file size cannot exceed 50 MB, and uncompressed file size cannot exceed 250 MB. And another thing to note here is that if we upload a zip from here and if it exceeds the size of 10 MB, we won't be able to see this code editor here. And a more elegant way to add external libraries is by adding a Lambda layer. A Lambda layer is also a zip file that is available to the function, Lambda function, but that zip file is not loaded in the same directory as Lambda function.py file. Instead is mounted onto the op directory of the Lambda file system and is accessible through there. Now we will try to create a geocoding service, and for that we will create a Lambda layer with ArcGIS Python API library. Let's take a look at how we can do that. Let's open a command prompt, and for Lambda layer that a Python Lambda function can load, the library packages needs to go into a specific directory structure. And also, since we have a limitation of 50 MB on the zip size and 250 MB on the uncompressed size of the layer, we will try to install just the minimum requirements for geocoding service with ArcGIS API. So let me install the ArcGIS Python API without any dependencies, and I'll set the target to the required directory structured for the Lambda layer. Alright, the ArcGIS library is now installing. Okay, it's successfully installed. Now I'll add other dependencies. We'll install UJSON in its respective directory. Alright, after that is installed, we have these three requirements that are necessary and that are written inside a requirements file, so we'll install it from there. Alright, this error is because we haven't installed all the dependencies for ArcGIS Python API, but this should be fine for geocoding application. Now let's zip the created folders. Alright, now we'll head back to the Lambda function and create a layer. Let's name it ArcGIS Geocoder. Let's upload the created zip file and we'll select the runtime as Python 3.8 and then create. Okay, the layer has been created now. Now let's tag that to the Lambda function. Alright, we'll click on layers, add a layer, custom layers, choose ArcGIS Geocoder version 1 and add. The Lambda function is now successfully updated with the Lambda layer. Now let's update the code here to accept a string address and then geocode it into XY coordinates. Alright, since we've added the layer, the ArcGIS library is now available to the Lambda function. And for geocoding, we will import from GIS module, GIS method, and geocode method from geocoding module. And then in the Lambda handler, now the custom attribute that will pass is an address string. We'll create a GIS object and then geocode the address string. And we will pick the first result and get the location attribute from the result. That should be the XY coordinate for the address string. Let's deploy this function. Alright, the function is now deployed. Let's update the call, API call. We'll pass address string as New York Street, Redlands, California. Let's call the API. And we can see here that it has returned the XY coordinates of the string address provided. And with this, we can see how we can make external Python libraries available to the Lambda function and how we can create a useful geocoding service using AWS Lambda and the ArcGIS Python API. In the next demo, we will see how we can still deploy our Lambda functions when our dependencies doesn't fit into the specified zip package size limits. In this demo, I will be deploying an address classification service on AWS Lambda to classify addresses into their respective countries. This address classification is done by a deep learning text classifier model, which is created from ArcGIS Learn module. And the deployment packet size for this application exceeds the 250 MB size limit of the zip package that is supported by AWS Lambda. So in order to support this service, we will be creating an AWS Lambda function based off a container image. First, we will start by creating a container with all the dependencies required for text classification. So this is my container Docker file. I'll go through the Docker file. We first pull the public ECR Lambda Python 3.6 image, and then we copy the requirements file into the temp folder. Here is our requirements file. So these are the requirements that we need for text classification workflow. Going back to the Docker file, then we will do the installs, pip installs, and then finally we'll install Torch and Torch version, but the CPU version, since AWS Lambda doesn't support GPU. Then finally we'll copy the code files, utils.py and textclassifier.py into the Lambda task root directory, and we set the entry point of this Lambda function as textclassifier.lambda handler, which in the previous examples we were setting as Lambda function and Lambda handler. Finally, we are also setting a transformers cache environment variable, which is required for the transformers library that is a dependency for this workflow. Okay, now let's use the Docker file to create our image. We'll open a PowerShell. Alright, in the PowerShell, first step that we'll do is we'll build the Docker image. Alright, Docker image is built now. And now in order to use this image with the AWS Lambda function, we need to push this image to our private repository on the AWS. I'll just show you how to do that. This is our ECR service under AWS Lambda, and for pushing the image here, we will create a private repository, and I already have created ArcGIS 183 as my private repository, so I won't be going through with this step. And then we will have to push our image to this particular private repository, and we can view the push commands. We first log into the this private repo. We complete the authentication step. Then we have already done this where we have built our image, and then here we tag the image to this particular repo, and finally we push it to the repository. Now let's go back to the PowerShell. We have already built the image. Let me complete the authentication. Alright, and the authentication is done now. Now we will go ahead and tag a Docker image to the private repo, and then finally we'll push it to the repository. Alright, and the push is complete now. Now we'll go ahead and create a Lambda function. We will click on create function. This time, instead of starting from scratch, we will be starting with a container image. We'll name our function and then browse to the image that we just pushed. And since our function will also be writing or caching the model weights into the S3 bucket, we will need to provide a role which have access to S3 bucket, which has read-write access to S3 bucket. And then we can go ahead and create the function. Alright, the Lambda function has been created now. Now we will modify some settings in the Lambda function. Since it is a deep learning prediction workflow, model prediction workflow, we will increase the memory of the Lambda function because it will need more memory for predicting through the model, and it will also take more time. So we will set the timeout to 1 minute and save. After that, we will create a trigger. We'll add an API gateway. We will create an API, REST API. We'll keep the security open and say add. Alright, the trigger has been added now. Let's look at the endpoint. Alright, we have copied the endpoint. And before we pass any attributes to the API gateway, let's take a look at the function code. So this is the text classifier.py file that we have pushed to the image. This function, the Lambda handler function, expects a model bucket where the model weights will be cached, a model ID. This is an item ID for a trained text classifier that has been trained to classify addresses, and it expects a threshold for classification, and it expects a text list, which is a list of addresses separated by /. And now let's make the call to the API using the Postman client. We will paste the endpoint and we will pass the params. We'll pass the model ID, and the model ID will be an ArcGIS online item. So this is our item. We'll take the ID, we'll pass it here, then we'll pass model bucket. So I have a bucket named ArcGIS model, just learn models. Then the threshold, let's pass it as 0.5. And the text list, which is a list of addresses separated by /. Let's pass to address to the classifier, and let's hit send. And the addresses have been classified. The first one has been classified as a French address with a confidence score of 0.55, and the second one as a Canadian address with a confidence score of 0.85. So this is how we can deploy a deep learning model using ArcGIS Learn API onto AWS Lambda with the help of container images. Let's do a recap of the session now. We saw various ways to deploy Python scripts as services. We saw how to deploy services within ArcGIS ecosystem, on your own infrastructure, or on cloud infrastructure using Heroku and AWS Lambda as an example. We also saw ways to integrate various ArcGIS apps with ArcGIS API for Python. Also went through an example of integrating third-party Streamlit application with ArcGIS API for Python. And here are some further learning resources from the session. Thank you.